this is the periodic table. Okay, so here we have the elements starting from hydrogen, the helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, then sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, then potassium, calcium, scandium, titanium, vanadium, chromium, manganese, ferric, that is iron, then cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, krypton. Then we have rubidium, strontium, yttrium, zirconium, niobium, molybdenum, like this. This is our periodic table, right? So in this periodic table, the first two columns, these first two columns are known as S block elements, right? So these two, okay, these two columns are called as S block elements. Why? Because their final energy state, right, final orbit, the electron is finishing with S. So if you take hydrogen, that is 1s1, right? If you take lithium, that is 1s2, 2s1. If you take beryllium, that is 1s2, 2s2, right? If it is sodium, 1s2, then 2s2, 2p6, then 3s1, right? So since the electron orbitals, the last orbitals, are finishing with S, right, this is called as S block elements. The first block would be finishing with S1, so 1s1, 2s1, 3s1, 4s1, 5s1, like that. And this one, second column, the orbital is finishing with S2, so 2s2, 3s2, 4s2, like that, right? So these two first column elements are called as S block elements. And this first column, it has the name of alkali elements, and the second column, it has the name of alkali earth elements, or we call it as metals also. So alkali metals and alkali earth metals. All right, so here you see 1s1 hydrogen, right, helium 1s2, so finishing with the S block. Then it comes to lithium 1s2, 2s1, and beryllium 1s2, 2s2, right? And then these all are p block elements, since the electron is orbital is finishing with p. Then again we have sodium 1s2, 2s2, 2p6, 3s1. Then we have magnesium, that is 1s2, 2s2, 2p6, 3s2. So this which is in the ash color is the last orbital, right? So since it is finishing with S, we got it as S block elements. And these elements, right, which are here, we call them as P block elements, right? So these over here, these are called as P block elements because their final orbit is filled with P electrons, right? P block electrons. And in between these two, there are certain number of elements, right? These we call it as D block element, right? These all will be called as D block elements, right? They are called as D block elements, or we call it as transition elements also, right? Right, usually we call it as transition elements also. And here you see, right, what I am showing on the point, right, this region and this region, certain number of elements commonly mentioned here, right? So this is not an element, as like if you see here we have potassium, this is calcium, this is carbon, and this is nitrogen. These two boxes are not like that, right? These two boxes are not like that. These two boxes are a number of elements. So this one and this one, we will have another box which would be drawn separately in any periodic table, right? There would be two rows and 14 columns, right? So this is actually fill in this part. Okay, we usually draw this particular F block elements into separate. Otherwise, what will happen if we fix them into here? This periodic table will be going too large, right? So it is going to be like this much length. Why? Because if I insert these elements, these two elements, first two blocks will be somewhere here, right? Then I have these elements right at the bottom, so that will have some space. Then I have these many elements, so that would be coming somewhere here. Then I have these elements, so that will be appearing something like this, right? So your periodic table is going to be too big, difficult to draw. So that's why what we do, we draw this S, P and D elements into one set and F elements into separate column, right? F element into separate column and row, right? So we draw F element into bottom side. So it is not shown in this figure, right? It is not shown. For us, it's not necessary also, right? So this is how we draw the periodic table. And now we'll see the valency. The first block which we are showing here, it has have one electron excess, so that will tend to give that one electron, right? Tend means possibility to give. In the same way, this one, right? The second last row, right? Second last row, this row, it has usually 7 elements on its last shell, right? So I will put number 7 in order to show that I am discussing about the 7th block element. So 1, 2, 3, 4, 5, 6, 7, right? So this column actually I am talking about. So this does have 7 elements in the last orbit, right? They tend to be stable, right? They tend to be stable. So in order to be stable, this one has extra 1 electron. So what will it try to do is, it will send that electron out so that it can gain the 8, that is inert gas configuration, right? So inert gas configuration is having 8 electrons in the last shell, right? So not only 8, so the number of electrons which can be filled, as much as electrons if it is filled, then it does not need any electrons. So these elements, they don't have any excess elements, they are not in the need of electrons, and they are not in the need of electrons, so they are stable, right? So they don't need electrons and they are not going to give any electrons, they are stable, right? So in order to achieve this stage, right, this inert gas stage, all the other elements will try, right? So by gaining 1 electron, this will achieve this stage, right? By allowing 1 electron to go, this one will achieve this stage, right? So this is by gaining 1 electron, and this is by allowing 1 electron to go, right? Right. So that's why it's written accept 1 electron, right? Accept 1 electron. So what we see, this one need to give electron, and this one is in the need of electron. So combining these two, a usual phenomena will happen. This element will give the electron to this element, okay? Because this element need electron and this element has excess electron, right? So this excess electron will be given to this one. So that one will come here and filled, right? So now it has 8 electrons in the last orbit. this first block elements, they are excess in one electron, will give away that one electron to those who are in need of that, right? So this seventh block element, they can accept one electron, right? They can accept one electron. So this one will give that electron to this one. So now it has 8 electrons, right? So now it is fine. It achieved the inert gas status, right? Similar way, this one also, it has extra one electron. So if this one give that electron, it does not have any electrons in the last orbit. So this is going to be its last orbit. So this also fine with that giving of the electron, right? So now these two are going to achieve the inert gas status, right? So this is why we need the valence number. So both of them, the valency is 1, right? So whether it is achieving accessing an electron or whether it is giving out an electron or receiving an electron, the valency is 1, right? So for valency, we will not put any minus or plus 1 or minus 1, right? So just 1. While we are drawing in the diagrams, if it is giving electron, we will write like plus E, and if it is accepting electron, we'll write minus E. That is different story. But for the valency, right? For the valency, how many electrons are transferred, whether gain or lost, that is fine. If it transfer 1 electron, then valency is 1. If it transfer 2 electrons, then valency is 2. If it transfer 3 electrons, then the valency is 3, right? So this is how the valency number 1 is achieved. This is our second column, and this is our sixth or second last column, not second last, third last column, right? So if you see here, what is written, give up 2 electrons, right? So this will give away 2 electrons. If I take magnesium, right, so I will take an example of magnesium. So magnesium, what's the atomic number? 12, right? So in the first orbit we have 2. Then in the next orbit, how many we have? 2, 8, 2. Okay. So 2, 8, and I have 2. What is the atomic number of the neon? Neon is here, okay? You're not gas, neon. 10, right? So how will we write that? 2 and 8. This magnesium is there, right? So what will that do? That will give up 2 electrons, right? And here we have this sixth column, right? So sixth column in the sense 1, 2, 3, 4, 5, 6, right? So I'm talking on the normal index number, not counting the Roman number here, right? So this one accept 2 electron, right? This one will accept 2 electron. So we will draw for oxygen, right? We'll draw for oxygen 2 and 6. So when we're talking about this magnesium, it will give up 2 electrons, right? It will give up 2 electrons. So this electron and this electron will be given to somebody who are in need, right? So when these 2 electrons left magnesium, there won't be any electrons in this particular orbit, right? So which means this orbit will become the last in this case, right? So these 2 electrons will be given to somebody who are in need. This oxygen, that will accept 2 electrons, right? That will accept 2 electrons. So what will happen? These 2 electrons which are given by magnesium will go and fill the oxygen, right? So if these 2 will come and fill the oxygen, now oxygen have already 6 electrons in the last orbit. Magnesium gave 2 more electrons, right? So that is 8 electrons on the last orbit, right? 8 electrons on the last orbit. So I will draw it in different color. So these 2 are the electrons given by magnesium, and these 2 are the electrons of the oxygen itself, right? So now if you see the oxygen, it has 1, 2, 3, 4, 5, 6, 7, 8, right? 8 electrons in the last orbit. If you see this oxygen and this neon, now these two seems to be similar, right? Neon also have 2 electrons and 8 electrons. Now oxygen also have 2 electrons and 8 electrons, right? So now the electron configuration of neon is similar to the oxygen. I will write oxygen 2 minus because it is an iron now. It gained 2 electrons, so now it is an iron, right? If you see here, neon, the electron configuration of neon is 2 and 8 is equal to the electron configuration of magnesium, right? 1, 2, this also have 2, and the next shell 8, next shell 8. So these shell electrons are already given, so now no electrons in that shell. So the neon's electron configuration is equal to the magnesium ions electron configuration. I will write 2 plus because it give 2 electrons, right? Neon, if you see, it is a stable element because it's an inert gas. So stable elements are the inert gases, right? So usually they don't go for any reactions. Similar way, this neon, now the magnesium 2 plus and oxygen 2 minus ion achieve the status of the neon, right? So we will combine this Mg2 plus and O2 minus into MgO, right? So this 2 plus and this 2 minus will be cancelled out, so to become 0. So this is not actually mathematical numerical system. I'm just saying in a way that you can understand easily, right? So this 2 plus and this 2 minus 0, so MgO, right? So this MgO is now stable, right? Very stable. Why? Because it achieved the electron status of the neon, right? So this is actually what happened in the reactions. The electrons or the elements try to get the stable state by either receiving or leaving or by sharing the elements, right? So this is how the stable state achieved, and that is what the minimum energy state, right? So whenever it has 6 electrons, always it will tend, okay, can I achieve one element, 1 electron or 2 electron, whatever it is, right? Similar way, magnesium also will try to give up those 2 electrons. But in case if they achieve this inert gas state, they would not be looking for anything to give or gain, right? Now they are stable, right? So this stable state is the minimum energy state.